But since physics is an experimental science, two of the lectures in the school are from experimentalists. And today we're starting Eilam, who will discuss the hunt for the Higgs. And since he's co-convener of the Higgs search group, right, Atlas,
yeah,
he will give us the lowdown on the discovery, the recent discovery
or non-discovery
of the Higgs.
Thank you. This is a great honor for me because the first time I've been here was as a student of Nati in 1984, the same year that you mentioned. And that were strings at the time. And it took me 17 years to come here and give the talk. Okay, so I learned something this morning, okay? The David Gross test, okay? It's got, first of all, to make sense. And it does. It's hard to modify, look at technical, it didn't get us anywhere. So it works, but does it really work?
Sorry, what is it?
It is this. Okay, so just a coincidence, I also chose to start with Rutherford. 1911, the discovery of the nucleus by Rutherford. Took us exactly 100 years to have 200 million protons collide with each other per second at the LHC in search for the elusive Higgs boson. Now, the outline of my talk is made actually of, it's very simple. I think for you it's better, it's a bit darker. I try to make only the, because you will miss the beautiful events. Okay, now it's good. So, November 15, 2011, we combined for the first time in history Atlas and CMS, and that was based on the lepton-photon data sets of 2.3 inverse femtobarn. Less than a month after that, we had the seminars at SEM by Fabiola and Guido. The seminar of Fabiola described the Atlas, and that will be, most of my talk will be based on the Atlas, since as was said, I'm the Atlas Higgs convener, so that's what I know best, so that's what I'll talk to you about. And, but I will also show the results of CMS for reference, okay, and I'll compare them with Atlas so you get an idea and you'll be able yourself to make the comparison and see if you believe that what Atlas has seen is a discovery or not. You'll be able to make this assessment yourself. So, November 15th, first of all, I hope that one thing that will come out of this lecture today, and actually I worked in the last hour to make it, because when I saw the audience, I understood that the thing that I should do is not what I prepared, but I should make sure that each of the students here will know how to read these plots. So never mind what's in this plot now. In November 15th, we knew that the Higgs cannot be between 141 to 476 GeV. So if you believe in a light Higgs, it should be below 141 GeV. That was the result of the November 15th. If you look at the paper of the November 15th, and you'll see that the references, there are 6 references that go from paper to paper, and we copied them from paper to paper. And believe me, there were lots of arguments in the collaborations, which references to put here for the Higgs, and why do we call it a Higgs boson. So, in 1895, the father of the discoverer of the electron, G.P. Thomson, who won himself a Nobel Prize in 1938, says that the goddess of learning is fabled to have sprung full-grown from the brain of Zeus, as you see here. It is seldom that a scientific conception is born in its final form on a single parent. That must be the case here. In the Wolf Prize, 2004, Higgs didn't come, but you can see Brout, who died about 2 months ago, I think, and Engler. So I was a bit worried, a bit bothered that Higgs didn't come. So I dared to write him, and then I dared to go and see him. And then he didn't come to see me after he invited me over there, by the way. So I gave my seminar in Edinburgh. I came back to Israel, and then suddenly a year ago, after a few years of silence, I get a letter from Higgs who answers all the questions that I gave him. And one of the questions was the history, and that's, according to Higgs, the history of the Higgs. So actually, he also mentions that Engler, Braut, Higgs, Guralnik, Hagen, and Keeble. He writes to me, note that all 6 of us were awarded the 2010 Sakurai Prize of APS. He didn't come to this ceremony as well. That's Keeble, which we saw the picture in David's talk. We saw the picture of Keeble, Guralnik, Hagen, Engler, and Braut. So the spontaneous symmetry breaking was first introduced by Ginzburg and Landau in 2 papers, 1950 and 1957, in an attempt to explain superconductivity. The idea is that the physics of the system, the Lagrangian, possess some exact symmetry, but the vacuum, the ground states, break this symmetry, as you can see in this picture here. It was Nambu in 1960 that proposed for the first time that spontaneous symmetry breaking is the source of fermion masses in elementary particle physics. When I looked at the paper, I was astonished to read there that he writes there. He was talking of superconductivity in this, but the existence of such a condensate scalar field would break the symmetry of the model. And he writes, in particle physics, that would be a non-abelian group containing the human group associated with electric charge conservation as a subgroup. So that's Nambu. Inspired by Nambu, Goldstone in 1961 studied models featuring scalar fields and finds that all these models contained under spontaneous symmetry breaking massless bosons, which are called the Nambu-Goldstone bosons. And then Goldstone, Salam, and Weinberg proved in 1962 formally what we know as Goldstone theory, actually, that Goldstone boson must occur when a symmetry, and at that time they were talking about isospin or strangeness, is broken. But no such bosons were observed experimentally, and that was a bad thing. So Weinberg recalled in his Nobel lecture, which I really like to read, that he was disappointed when he wrote this paper that he added a quote to the paper which the publisher took away, but he added a quote from King Lear, nothing will come out of nothing, speak again. So there was a big frustration. Is quantum field theory a one-trick pony that can explain only long-range forces, so can we do something with it? Philip Anderson in 1963 points out that in a superconductor, the Goldstone mode becomes a massive plasma mode due to its electromagnetic interaction. And actually, he claims to be the first one to talk about Higgs mechanism, etc. He himself. Peter Higgs, physics letter, July 1964, shows that one can evade Goldstone theorem. He shows that if the broken symmetry is local gauge symmetry, like electromagnetic U1 gauge invariance, then although the Goldstone bosons exist formally, and that's what you learn actually in undergraduate, and in some sense real, they can be eliminated by gauge transformation so that they do not appear as physical particles. That explains why experiment failed to detect the massless bosons, and that's how you evade the Goldstone theorem. So that's what we learn actually in the first year, in the 3rd year of undergraduate or 1st year of master studies, that the missing Goldstone boson appears instead an helicity zero state of the massless boson, which thereby acquires mass. And you know this sense that the photon eats the Goldstone boson and acquires mass. But the interesting thing is happening now. Based on field theory using a Lagrangian formalism, Higgs develops the formalism of the mechanism by which the Goldstone boson is eaten, as I said. And he writes it in 3 pages paper, and he sends it to physics letter. The paper is rejected. Higgs writes in the letter that he wrote me, I was rather shocked. I did not see why they would accept a paper that said this is a possible way to evade a Goldstone theorem, there's a possible way, and then they reject a paper where I show how to do it. But then comes an interesting thing. Higgs add an epilogue to the paper, the last part of the paper, you can check it yourself, and he writes there, it's worth noting that an essential feature of this type of theory is the prediction of incomplete multiplets of scalar and vector bosons. So he predicts the existence, he looks at the leftover degrees of freedom, not the one that around the circle, but the one that goes like this, the harmonic oscillator that has a mass, the Higgs boson, and send the revised version to PRL. The referee, he says, who I discovered later was Nambu, drew my attention to a paper by Engler and Braut that they had just published in Physics Review Letters. Higgs is asked to cite Engler and Braut, and the paper is accepted in August 1964. Then Guralnik tells in 2009, as we were literally playing the manuscript, placing the manuscript in an envelope to be sent to PRL, Keeble came into the office bearing 2 papers by Higgs and by Engler and Braut, that just arrived in the very slow mail of our institute and in the Imperial College unreliable mail, and we were very surprised and even amazed. Later he says that they gave references to Higgs, Broughton, and Glare. Maybe the right thing for them to do would have been to write down there that after completing the word we received, etc., etc. Anyway, in 1964, right after Higgs, they published that thing, and Higgs wrote in his mail to me the following sentence. In my first paper, I outlined how to evade the Goldstone theorem, and Glare and Bout showed how a gauge field interaction turns Goldstone massless boson, elementary or composite, into elicited zero states of massive spin 1 particles. They started from Feynman diagrams and didn't discuss the remaining massive spin 0 particles. In my second paper, I used lagrangian field theory explicitly with elementary scalar fields a la Goldstone coupled to a gauge field, so the massive spin 0 boson was an obvious feature to which I drew attention. The story ends with the following thing. Glashow in 1961 suggested the symmetry of the electro-weak interaction with SU2 cross U1 and is broken to U1 electromagnetic, but Glashow put the masses of the force carriers by hand, and his theory is therefore non-normalizable. Weinberg in 1967 implements Higgs mechanism to the Glashow's SU2 cross U1 and writes the most quoted paper in the history of particle physics. Now I want to ask you, most quoted paper, how many quotations do you think that Weinberg had? What is most quoted in particle physics? 6,000? 7,000. 7,500. So where it's V. So 1,100 for Bob Cousins is really a lot.
Eilam, a small comment. In 1965 or late 1964, Migdal and Polyakov, who were then 18 years old, independently of everybody else, invented the Higgs mechanism.
I heard it, I checked it, I couldn't see it, sorry. So,
Here is the paper.
okay, fine. Good, I learned everything from everywhere. Okay. Anyway, we are over the Higgs now, we go on, okay? One would predict that the mass of the weak interaction force carrier is 80 and 90 GeV. As you know, it took 14 years to discover it. He spends a lot of his paper talking about renormalizability. He believes that it should be renormalizable, but he doesn't know at that time how to do it. And it took a few years until Truft under Weizmann proved that he was his supervisor, etc., proved the normalizability of the Young-Mills theories with message generated by spontaneous symmetry breaking in 1971. So all that is left to find now is the mass generator of the Higgs boson. Everything is very nice, but does it work? So
the Higgs boson, the scale of particles already been observed.
Yeah, I know this, because you see the masses of the Z and the W, right?
Well, you see those polarizations.
Yeah, okay. I know this. You see, I even know this. But okay, so let me remind, because we are still, most of us are students here, including me. So a mass term is given by m psi bar L psi r. Only left-handed fields carry weak charge. So via spontaneous symmetry breaking, the Higgs field kind of charges the vacuum with a weak charge. That's the way that Eliezer explains it, and the symmetry is preserved, hidden. So if you work out the mathematics, which is very simple, you get actually the important thing for me now in this lecture, that the coupling of the Higgs to particle is proportional to the particle's mass. Just a second, where is that? So the Higgs boson will therefore decay with a higher probability to the heaviest particles kinematically available, because the coupling will be, for fermion, it will be the mass of the fermion over the vacuum expectation value, which is around 250 GeV. So the question is, the engine, what is the engine of the Higgs is kind of the engine of the Standard Model. So if you describe the Standard Model as the car and the accelerator as a racing car that tries to hit this one and look at the anvil and explode the engine and check the engine, then that's what we are doing. We are now trying to explore and learn the properties of this engine of the Standard Model, which is the Higgs boson. It's also the only missing piece in the puzzle of the Standard Model as is. Of course, you see that the pieces don't sit together very well, but that's for the future. So the accelerator, the LHC, 27 kilometers, 150 meters below ground, and the border between France and Switzerland. So we have 50 nanosecond proton bunch strand with about 6 to 20 proton-proton interaction per bunch processing. So you'll see in a second what it means. We'll get to it. What does it mean that we have about 20 interactions per bunch crossing? But the luminosity, 2011 was a fantastic year for the Large Hadron Collider. The total collisions, we had 350 trillion collisions. When it was translated to luminosity, we had a recorded luminosity of 5.2 inverse femtobarn. I remember that we were talking about having, I told my student, I remember one of them, I told her, I remember, you'll have 5 inverse femtobarn by the end of 2012. So we have it by the end of 2011, and we expect to get another 15 or so next year, and perhaps in a higher energy of 80 TeV per 80 center of mass per experiment. So this is really amazing. You see how fast we went from EPS in July, lepton, photon here, and now at the end of the year, that's where we are. And the data taking efficiency is about 94%. It is really, really, really amazing. So this is what we deal with. Now, while I'm talking, you can count how many interactions you see here. I managed to count about 18. There should be 20 here, okay? So this is one collision, okay? And this is a Z goes to mu mu, okay? A Z decays into pair of muons. And we are supposed, and that's a simple process, okay? And we have much more complicated processes, including missing energy, including jets, and all this. And we are supposed to be able to tell from this mass, that's from CMS, that's from Atlas, from this mass, which is called pileup, we are supposed to kind of filter out what is interesting. And that's only one collision, okay? And every collision looks like this, and it becomes even worse and worse as we increase the rate of collisions. And we have also what we call out-of-time pileup. We have pileups, collisions that occur, since everything occurs so fast, we sometimes see here traces of things that occur in the previous collision.
Is this typical?
You know what's typical, right? So it's very typical. No, but it's not typical, but typical would be 7, 8. So I think it's also quite impressive that. But as you can see, sometimes it becomes very easy to spot the thing. Okay, that's the Z, so we are talking about a few centimeters here. The whole thing, yeah. You'll see the resolutions. The detector gives you the resolution. With just the electromagnetic calorimeter, we get a resolution of 1.5 centimeter in Z, because we have a pointing geometry, but that's only for Atlas. Okay, so that's a detector. Okay, we have students here, so I need to go over this a little bit so you understand how it's made of layers, okay? So you have an interaction, and then you have a detector, pixel detector, which identify. I'm talking about Atlas because, but it's very similar in all detectors, including I worked in the past in Opal, Delphi. Everything is the same. So we have charged particles detectors. Then we have electromagnetic detector, hadron detector, and muon detector. So it goes like this. If you have a particle that goes all the way and is identified by the charged particle detector, and then deposits some DE to DX, some minimum ionizing into the electromagnetic and hadron calorimeter, goes all the way out, that's a muon. If you have something that actually you see it in the charged particle and then deposits all its energy in the electromagnetic calorimeter, that must be an electron. If you have something that you don't see, an electron where you take off the charge tracks is giving the traces similar to a photon. And then we have, of course, a proton, which will leave traces in the charge and the electromagnetic, and then will completely be absorbed in the hadronic calorimeter, and the neutron, which will be absorbed in the hadronic calorimeter, but leave no traces in the charge and electromagnetic. So that's the principle of a detector. Why doesn't it? Okay. This is, it's boring now to show the usual pictures, so I try to look for different pictures. If you go to building 40 at CERN, which is the building where one side is Atlas and another side is CMS, so CMS gave us a present about half a year ago. They put on their wall a huge, huge poster of CMS, so we work in the Atlas side and we always see the CMS, and we go and take pictures there, as you can see. And, but you see, again, the detector, that's how it's built. You have the charge, the electromagnetic, and the muon. Now, that's a one-to-one, because their detector is much smaller than Atlas. But, so Atlas took an American artist who actually painted on the Atlas building, the Atlas detector. So this is a painting, okay? On the Atlas building, these are the trash cans and the stairs. And we work, the control room is inside here. That's where we work, okay? So that's beautiful. Again, you see the structure of the layers, okay? The charge pixels detector, like many CCDs, and the electromagnetic, and these are magnets, and the outskirts you see the muons. So when you look at such an event, that's a visual, okay? That's a visual of an event as it's seen by the computer. It's not much different in my view than a picture of me that you look at it now, because your brain is transmitting what the photons come back from me into your eyes, and you create a visual in your brain. So it's not different. We take pictures of the events that occur in the collision, and these are very complicated pictures. We are supposed to be able to identify electrons. Now you know how we identify electrons, charge and electromagnetic. We are supposed to identify muons that goes all the way here. We are supposed to identify, we can make a balance of the energy in the transverse plane, since we don't really know the collision in the z direction, because it's not the protons that collide, it's the quarks or the gluons inside the protons that collide, and you never know where they collide, but you do know where it collides in the xy plane. So you can really make a balance in the xy plane, so you can find the direction of what we call the transfer energy, missing energy, so you can actually calculate it. Quarks, as you know, don't appear free in nature, so they manifest themselves as jets. So we see jets, and you can see traces of the jets here. You see jets here, jets here. Bottom quarks will look as bottom jets, but since the bottom quark has a lifetime, you can actually measure the lifetime, and you know it's a bottom quark. And of course, you should be able to tell the primary vertex from the various pile-up vertices that you see. So I hope that I kind of went over all the ingredients, all the objects. Higgs production, there are four processes, main processes we consider. There's the gluon-gluon fusion, of course, which is 10 times bigger than what we call the vector boson fusion. You see, this is picobarn, okay, this thing here, which is much bigger than the associate production of a Higgs with a vector boson. And the smallest one is the TTH production, and it's also very difficult because of the multi-jet environment. So Higgs decay. The Higgs boson decays to the heaviest kinematically available particles. A light Higgs, and by light, remember that the lab has already left an heritage, which is that the Higgs is heavier than 114 GeV. So for us, a light is everything between 114 and say 130 or something like before the ZZ and WW starts to go into the game. So a light Higgs decays to tau tau and mainly to BB. But Higgs to BB is hard to detect or trigger. It's jets. We have an environment where most of the collisions give us jets and jets and jets, so we cannot tell the background from the signal. So it's very difficult to detect the Higgs to BB. So the only way to detect Higgs to BB is when it's producing an association with the W or Z. This is something we work on, but it is very low cross-section times branching ratio. Electrons and muons and photons are easy to trigger on. You see a clear electron, a clear muon, or a clear photon, and you trigger on it and you register the event. What I forgot to say is we have 200 million collisions per second, but we cannot write down that many collisions. We cannot. We can write down only something like 200 events per second, something like that. That's not a lot. So we have to filter 99.9999%. We have to filter out and throw them away. And one thing we want to make sure that we don't throw away a Higgs boson. So we want to trigger on the important events. We don't know if a Higgs is there, but we don't want to kind of throw away a Higgs boson. So it's a very sophisticated trigger system in both experiments, ATLAS and CMA. Electrons, muons, and photons are a good way to trigger. You don't want to miss these events, and you'll write them down. So what do we do with photons? The Higgs will not couple directly to photons. Photons are massless. The branching ratio of Higgs to gamma gamma is 10 to the minus 3, and the miracle of all miracles, it turns out that the Higgs to gamma gamma is actually the most sensitive channel for a light Higgs between 110 to 120 GeV when you have this triangle diagram. Now, once the Higgs, the Z and the W start to open, you don't need both of them to be on shell. It's okay if one of them is on shell only. So once that happens, you can detect the XY, it's decay to ZZ. Of course, the ZZ will in turn decay to, for example, to 4 leptons. So look how clean is this channel. You see 4 clear electrons. You can reconstruct the mass of each pair, so you can identify the Z, which is on shell. You can construct fantastically the mass of the Higgs with a resolution of about 2 GeV. And this is a fantastic channel, and the so-called fluctuation that we see in Atlas came from 2 channels, from the gamma-gamma and for the 4 leptons. The same 2 channels are the important channels also in CMS to tell something about the Higgs. Nobody will dare to say I discovered the Higgs based on WW, because the WW will always be accompanied by a neutrino, because if it goes to 4 quarks, you can't do anything with it. You don't have resolution, you don't have trigger, you don't have anything. So you will either look for a W goes to lepton neutrino and the other W goes to a pair of quarks, but then you have missing energy. You can actually reconstruct this missing energy here, but you'll have huge background here. Or you can have 2 leptons and 2 neutrinos. Here you have a signature with large missing energy because of the neutrinos, but very, very bad mass resolution. So there's not much you can do with it unless you can say, I discovered, but you won't be able to tell what is the mass. Okay. Here's a new way, because we are bored already, to present the branching ratio of the Higgs. This is the mass of the Higgs. The color tells you what is the decay channel of the Higgs, okay? So if the Higgs is between 100 and 120 or whatever, the main decay channels will be the BB. You look at the color and you know. If you start to go here, you see that most of the Higgs at all this mass range will decay to 4 quarks. You see what is this color that dominates all this? That must be the lepton neutrino quark. But I told you that the most dominant channel in the low Higgs mass is the Higgs to gamma-gamma. Where is it here? It's this thing here. You see? This thing here? That Higgs to gamma-gamma. And that's a channel. That's the discovery channel, you believe it or not. That's the one. So what's going on here? BB, 4 quarks, LNQQ, they're all useless. They're useless, because if I look at this thing in a different presentation here, but I demand that I'll be able to use the channel, meaning I'll be able to trigger it and write it down. So the most efficient clean triggers, as I said already, are photon and lepton based. So that's what left, okay? If I normalize this, this is not even this is the real picture, because this is dominated by Higgs to tau tau and Higgs to lepton lepton tau tau. If both taus go hadronic, you can't do anything with it. The tau is not easy to trigger on. The tau is not easy to measure. So tau is not the name of the game. Now, in order to understand what I'm doing now, here is my first tutorial, okay? Some nanostatistical interlude to understand the yellow and the green bands. If you want to know how the yellow and the green band, we invented them in the around the year 2000, where we combined all the lab experiments. So we needed a region that is no alarm, that's the green. Then comes start to be alarm, that's the yellow. And then comes the region. But if you float in red, you see nothing, so we didn't. But you'll see in a second what I mean. So now you have to try and follow me, because I will really try to explain what's going on. So the average number of expected events is mu times S plus B. S is the signal. It depends on the mass of the Higgs. It's, of course, the luminosity times the cross-section times the efficiency for the Higgs. Mu is the signal strength. So it's the signal strength normalized to the standard model cross-section. If mu is 1, what you measure is standard model cross-section. If mu is 0, that's background only. If mu is more than 1, we found something like a Higgs, but with a much higher cross-section. If mu is less than 1, it could be SUSY Higgs, okay? Because we know that each SUSY Higgs, many of the beyond the standard model Higgs models contain a standard model light Higgs boson. So mu will be less than 1 there. Now we have 2 hypotheses. We have the signal hypothesis, which I call hypothesis mu, and the background only no Higgs hypothesis, which I called H0. Now if I reject the hypothesis H mu, I reject the hypothesis. It doesn't matter now what does it mean to reject. I reject it, I don't accept it. I exclude the Higgs with the mass mh. If the data is incompatible with H mu at mh at the level of 5%, later we'll try to explain what is incompatible, then mh is excluded at the 95% confidence level. That's what we mean when we say CLS is 5%. Again, the data is incompatible with the signal hypothesis at some mass at the level of 5%, which means that mh is excluded at 95% confidence level. Now, if I reject the background only hypothesis, then I claim a discovery. Not necessarily of a Higgs, but I reject the background-only hypothesis, I claim a discovery. If the data is incompatible with H0 at the level of 2.5%, then we say that we rejected the background-only hypothesis, we made a discovery at the level of 2 sigma. As David says before, 5 sigma means that the data is incompatible with H0 at the level of 2.7 times 10 to the minus 7. This is crazy, but you will understand it in about half an hour, I hope. So the key of all this is test statistic. Test statistic is a measure for the compatibility of an observed data with some hypothesis. It's usually constructed from likelihood ratios. I remind you the magic formula, n equals mu s plus b. A likelihood, by the way, of an hypothesis is the probability that given the hypothesis, I observe the data that I see. So a likelihood of h mu is the compatibility is the probability that given hypothesis with the signal, I observe the data. The likelihood of H0 will be the probability that given the hypothesis of no Higgs, I observe the data that I see. Now, the test statistics using the LHC Higgs analysis is the profile likelihood. I don't have time to go into details, but we wrote a very big saga about 40 pages explanation of all this, so you can look in the archive 1007 and 1727. So, let me see the situation. Okay. So the profile likelihood test statistics is what we do in order to tell everything. This is the formula for the profile likelihood test statistics. So as you see, it's a likelihood ratio. It's the likelihood. If I want to test the signal hypothesis, you test signal hypothesis when you try to reject it. You don't test the signal hypothesis for discovery. You test signal hypothesis only if you want to reject the signal hypothesis. So the only thing you can get out of testing the signal hypothesis is an exclusion. Okay? So you test the signal hypothesis. So mu is the relative cross-section to the standard model 1. The test statistics, which we call Q tilde, is minus 2 log of the likelihood of the signal divided by the maximum likelihood when we let the signal vary and let the background vary. B is the background, just background. A symbolic letter indicates the background, okay? Okay, so now I go and I actually, I constructed test statistics. The experiment, LHC, Atlas, say, or CMS will give me one number because this likelihood, if you remember, is the probability given an hypothesis to see the data that I see. So it's one number. But in order to know how frequent, how is this number that I get, does it make sense? Does it look like a signal or look like a background? I need to know what will happen if I will run LHC a zillion times. But I cannot run LHC a zillion times. It took us 2 years just to get 5 inverse femtobarn, okay? So what I'll do toy experiments, okay? I'll simply generate toy experiment, and I will look at the distribution of my test statistics, and I will get this chi-square that you see here. Now, this is the distribution of the test statistic under signal experiments. These experiments contain the signal. So most of the experiments will give me results which is here. If there is signal, if there is signal, if there is signal. Some of the experiment, even if there is a signal, will give me something that doesn't look like a signal, you know, fluctuation. So they give me this, they'll be very far around. This is the background region, this is the signal region. If I generate background-only experiments, this is the distribution of the test statistics. Signal-only experiments is like this. Now, this, if my result falls here, this is when I say that I reject the signal hypothesis. If this area here, if this is my observation, and this area here is about 5%, I reject my signal hypothesis at the level of 95% confidence level. Means, if there is a Higgs boson, I allow myself an error rate. I allow myself what we call type 1 error rate. I allow myself to be mistaken by this rejection by 5%. So I could be wrong. I could say there is no Higgs boson. In 5%, if I say that there's no Higgs boson at this mass, at the 95% confidence level, that means that I could be wrong. It could be that there is a Higgs boson. In 5% of my experiments, I will make this mistake. And by the way, let me tell you already now, in the just in November, October, November, yeah. In November, we said that we excluded 240 GeV in Atlas. And in December, we said we cannot exclude it anymore. Fluctuations, you know. Now, for those who lost me, Here is the way to do it in a very simple way, okay? Just remember, mu is the relative strength of the cross-section that you measure to the standard model. CLS measures the compatibility of the data with the signal hypothesis. If CLS is less than 5%, CLS is related to this p-value, this area that I showed you. If CLS is less than 5%, the signal hypothesis is excluded at 95% confidence level. Easy. Remember, CLS is compatibility. If CLS is very, very small, we exclude the signal. CLS is 1%, I exclude the signal at the 99% confidence level. Mu up is the signal strength for which CLS is 5%. That's what we call upper limit. If mu up is less than 1, now plug in this formula here, you get that the cross-section that we measure is less than the standard model cross-section. So if I put an upper limit on the cross-section, which is smaller than the standard model expectation for the cross-section, then my measured cross-section or my upper limit on the cross-section is less than the standard model, so I exclude the standard model. Higgs. So this is when we have this mu up less than 1, is exactly where we say that the mass of the Higgs is excluded at the 95% confidence level. So this is how it looks like. But before I show you this, they are called also Brazil plot because of the flag of Brazil. So if the expected number of signal events, that's what I put in an hour before because I understood who is the audience. If the expected number of signal events is so small that S plus B is about B, if this is this, I cannot exclude this signal. I cannot exclude it. Signal is too small. So the probability that I will see what I see if there is no signal is very big as well. So I cannot say that I can exclude the signal. So the first thing I do is I generate toy experiments with no signal. No signal. And I try to see what is the signal that I'll be able to exclude if there is no signal. So I get the dashed line. The dashed line is called the expected sensitivity of the experiment. Now, the mu equals 1. Below it is where I exclude, because that means that my observed cross-section is less than a standard model, or my upper limit on the observed cross-section is less than standard model. Above is where I can not say anything. So you see, that means that at the point, I think I put the lines. Yeah, okay. This point is the lower limit where from here I can exclude the Higgs. And there is the last point. So all this region here is my expected exclusion. So when you see expected exclusion from an experiment is from 125 to 400, that's what it means. It means that had there no been Higgs, you would have been able to exclude it. But if you see that the expectation is 125 to 400 and the observed is 130 to 400, you ask yourself, why? Why they could exclude 125, but they exclude only from 130? What is hidden? Is the red line here. The red line is actually what the data tells us. What does the data tell us? So when I cannot exclude with the sensitivity that I thought that I have, it means that I have an excess. I don't know if it's a signal, but I have an excess of events. It prevents me from exclude. Remember, every discovery starts with being able to exclude. Every discovery, always. Not being able to exclude, then it might become a discovery. So when you see that the observed is above the dashed line, you know, you read it as an excess of events. Here, here. When you see that your observation is below the dashed line, meaning suddenly you can exclude even more than your sensitivity, you have a deficit. So you're supposed to be signal plus background fluctuated down. There's a whole discussion about this, but I won't go into it. Okay, now, the question is, do we really have to generate a zillion Monte Carlo experiments, where sometimes if you do full simulation, it takes in Atlas 10 minutes to do one. So you need a lifetime of a few thousands of people to be able to generate. So we managed to, in this paper, which is called the CCGV, we found asymptotic formulas for all these things, so you don't really need to, so if you're in the asymptotic region, which we are now, then you can actually, without even one Monte Carlo experiments, know exactly what will be the result of a zillion experiments. So using this, you can show that actually the upper limit is related to the signal over square root of S plus B, of your significance. You can show it. And now, taking the background into account, we can tell the real story. We can say which channels really make the difference and which channels we are not sensitive to. So what is a background? For those who don't know what is a background. This is, for example, a Higgs production that goes to ZZ. But if you look here, you see that you could easily generate a dye boson. This we'll call ZZ plus jet, a dye boson from just a regular proton-proton collision. But both of them will have the same final state. How can I tell one from another? So this is the job of the experimentalist, to find sophisticated way to be able to separate this from this. But LHC has already, with 1/5 of the luminosity that we already have, measured all these background processes, possible processes. Some of them, like W, Z, TT, are already challenged for theory. Fantastic accuracy. The Higgs boson cross-section will be around here. It's similar to the dye boson production, WW, WZ, and ZZ. All these processes make background to the Higgs. All of them are measured already by the LHC, be it Atlas or CMS, and some of them to very high accuracy. So we understand very well our background, but all is left to do is to discover the Higgs boson. The background can spread from very high cross-section to very low cross-section, and the Higgs is around this ZZ, WZ, WW. That's where the Higgs is. So we have sometimes to go a few good orders of magnitude, 4 or 5 orders of magnitude, to tell the needle in a haystack. Sometimes I say it's like a needle in a needle in a needle in a haystack. So this the situation I was when I explained to you the trigger, but when I take the background into account, this is completely changing, and this is now the picture that LHC is working in. That's the environment of the LHC, and it took me 45 minutes to explain it. Okay, so for low mass, the most important channel will be Higgs to gamma gamma. This one is the channel where the Higgs doesn't even couple directly, has a 10 to the minus 3 because of the loop branching ratio, but is very visible, very easy to trigger on, very easy to measure. Then comes the WW, if the Higgs is 120 to 180, goes to lepton to lepton trino. As I explained, because of the missing energy, this is not a discovery channel. Then comes the ZZ to 4 leptons. You see, in this region, you don't have ZZ because here you have 2 Z's. You have 2 Z's produced on shell and serve such a big and make such a big background to Higgs to ZZ that we cannot do a thing with it. But here, when we are away from the ZZ resonance, when we are away from it, we can still use the ZZ goes to 4 lepton, which is called the golden channel. And at high mass, we have the lepton-lepton plus neutrino-neutrino, which is the dominant channel. But if I go back here, let me go back here. If I go back here, the low mass, which we call the lap edge, we have the Higgs to gamma gamma, Higgs to tau tau, and the VBB that can help us. I don't have time to go on everything. I will go to the most important one, which is the Higgs to photon-photon, where Atlas observed the huge fluctuation. So this channel has very clear signature. 2 energetic isolated photons, which create a narrow mass peak. So what you look is a narrow peak on top of a continuous smooth background. That's what you look for. You see the result already here, but we'll discuss it later. This thing here is 1-to-1 how a signal will look like if the Higgs had a mass of 130 GeV. So you ask yourself, oh God, how can they do anything with it? It looks like impossible. Statistics. So in order to be more sophisticated, we do very sophisticated things here. For example, we split the data into categories which are based on the direction of the photons. Why direction of the photon? Because direction of the photon tells you where the photon went in the detector. It tells you how much material the photon hits. And you know how much material, you know the conversion mode of the photon. Because the photon hits a material, it can convert into an E plus E minus very, very close by pair. And the resolution is degraded a little bit. And you need to know that you have a photon there that converted. Otherwise, you will lose it and you'll have less statistics. So you don't want to lose it. So what we do actually, we do a fit. In each of the category, we do a fit to this thing, an exponential fit to this thing, and we search for a signal on top of this fit. This is a picture of an event, say. What you see here is one of our candidates, one of our 70, actually I cannot tell you who are the 70. We have about 2,000 candidates, okay, because we cannot tell on top of the background which one is the Higgs. Okay, so we have thousands of candidates. So one of them will look like this. You have 2 photons. If you look very, very closely, And that's why I wanted to show you, because I want to give you a little bit feeling of what is to be an experimentalist. You see a pair of very close electrons here. Because of the magnetic fields, they spread out. But you see here a pair of electrons, and this is a converted photon, okay? It hit the material somewhere, and it converts itself into an E plus E minus pair, and you measure it. So this photon is under a category which is called converted central, because it means that at least one photon is converted, as you can see, and both photons are in the central part of the detector. So this channel requires very strict experimental aspects. We need an excellent gamma-gamma mass resolution to be able to tell that something is happening here, to observe narrow signal peak above the irreducible background, and needs powerful gamma to jet separation. And why is that? We have a lot of pairs of jets or gamma jets in the detector. It's very easy for a jet to look like a pion. A jet fragments, and actually many of the jets, it's enough that 1 in 10 to the 4, you don't need more than that, and then you kill your signal. 1 in 10 to the 4, 1 in 10,000 of the jets might fragment to a single pi 0, which then decay into gamma-gamma and looks like a photon. So what do you do with it? Look at the cross-section of the jet and the gamma jet and the signal. 40 femtobarn for the signal, and 500,000 femtobarn, for example, for jets, even more than that. You have huge, huge numbers. So if your fake rate is 10 to the minus 5, 10 to the minus 4, you're dead. You should be able to deal with this. You should be able to measure the fake rates from the data. This is a huge experimental challenge. But thankfully, Atlas has longitudinal and later electromagnetic calorimeter. I don't know if you can see it, but there's a lot of eta strips here. It's very hard to see it because the quality is not so good. So we are able to tell a photon, for example, from a pi 0. You see the pi 0 went to 2 photons, and you could tell it here. This pi 0 had a 21 GeV energy, and this one photon has 32 GeV, and you can tell the pi 0 here, which is fantastic. Now, to answer your question, because of this, we have a pointing geometry. And when we have a pointing geometry, we can actually find the Z vertex resolution. That's from Z to EE to be 1.5 centimeter, which is fantastic when you have 10 to 15 centimeters. So this one, here I talked about, here I talked about, each one of you knows in a second to prove this formula, that the Higgs mass, the gamma-gamma mass, is given by 2 times the energy of the first photon times the second photon, plus 1 minus cosine the angle between the 2 photons. So I was talking here about, I was talking before about the angle. That's where I talk about the angle between the 2 photons, that the pointing geometry helps us. And here I want to talk about the energy. And what you see here, actually, that the resolution that we have, this is from Z goes to E plus E minus, the resolution that we have is around, it changes, depends on which category, where you are in the detector, but it's around 1.7, it goes from 1.4 in the best case to 2.3 GeV width. Here you see how the resolution is affected. Mu is the number of interaction per beam crossing. That's the number of vertices that we counted. So you see here, it's, you see that we are very good. We can tell even the photon in an environment which is full of pileup. In a rich pileup environment, we can tell the photon. So it will not, that's why I call pileup a manageable nuisance, because we know how to deal with it. Now, we don't use Monte Carlo in order to tell the background, because you remember we fitted the data. But yet we want to make sure that we understand what's going on. So we use Monte Carlo to estimate our background. So here is a data versus Monte Carlo of what we expect from gamma-gamma, from gamma-jet, from jet-jet, and Drelian is here hidden. So this is the distribution of the 22,489 events of gamma-gamma that we measured. 71% of them are really photon-photon and determined from data control samples, not from Monte Carlo. Now, as I said, we fit each category and we look here. Here we do background subtraction. So if you look here, what you see is that sometimes your data is above the fit, sometimes below. And I think that you don't need a lot of imagination to see that something strange is happening here. We expect about, in this region of 125 GeV, we expect about 70 signal events with the luminosity that we have. About these 70 will sit on top of 3,000 events here. If you integrate this window here, you'll get 3,000 events. So the signal over background is about 2% here. This is, for example, just to show you that we made very thorough checks, okay? This is the different, 4 of the 9 categories that we have. If you look very hard, you want to see the peak at 126, but as you see, it's spread all over the peak. Here you don't even see it at all in this category. Here you see a little bit maybe. So just when we put it all together, we see something strange is happening there. If you looked only at one category, it will be very hard to tell that we see something. So how do you read this plot that was shown also by David? I hope that with my introduction it will be easier. Okay, so I stretch this background subtracted data here that we see. So the x is 110, 150, so you can look what's happening. The expectation, had there been no Higgs, we would have expected to see the red line Higgs. Now remember, when the observation is above the expectation, it's when you have an excess of events. When the observation is below the expectation and you are able to do a better exclusion, is when you have a deficit of events. So obviously, let's not hide and start with the main thing. You see a huge deviation of about almost 3 sigma here. The bands, the green and the yellow, are actually 1 sigma, plus minus 1 sigma, plus minus 2 sigma. What does it mean, sigma? It means that if I generate toy Monte Carlos, 68% of them, toy Monte Carlos without the signal. Toy Monte Carlos without the signal, 68% of them will sit in this green band. The median will be the red line. And 95% will sit in the yellow, all this region here. That's all it means. That's the meaning of the bands, the yellow and the green. Now, so of course, what you see here is something that only in about a few percent, even less than that, will occur, but that I will talk about it later. So you see, the excess here corresponds to this. The deficit that you see here, the beta limit that you do here corresponds to some deficit with respect to the expectation here. But the interesting thing is what happens at the lab edge. Lab had a limiter around 114 GeV, but Atlas, due to a fluctuation, a downward fluctuation, actually is able to exclude the Higgs between 114 and 115 here, because that goes below 1. That's the level of the standard model cross-section, and that's below 1 here. So this is excluded by Atlas data, and it's due to a downward fluctuation, which is clearly seen here. You see a downward fluctuation. You see that the data that you see is less than what you would have expected if there was no Higgs. So how can you explain it? You explain it by the fact that you have a signal plus background if there is a Higgs, and it fluctuates down. It fluctuates down so much that the probability for the signal to fluctuate down so much is less than 5%, so we exclude it. Some people, including myself, will tell you we don't like it, we don't want to enjoy, we don't want to benefit from downward fluctuation. But the statistical method agreed between both Experimental Atlas and CMS is to use CLS, which allows this downward fluctuation, tries to protect it, but sometimes doesn't do the job all the way to the end. So I would take this exclusion of 114 to 115 with a grain of salt. But I wouldn't take this thing with a grain of salt. Okay. If I compare to CMS, Atlas, CMS, you need a lot of imagination to see something here. Okay, but you do something. So it's very hard to compare them. You tell me I have only a half hour left? Really? Why? So let's put them one on top of the other, and now you can tell yourself what's going on here, okay? So Atlas is it's hard, not hard to tell. Atlas is the one behind, CMS on top. The red and the dash here are the sensitivity of Atlas and CMS, which are amazingly the same. Even the bands are almost the same width. So it's like doing the same experiment twice. One sees an excess around 124 GeV. Once is an excess around 126, both excesses are within the resolution. Now, let me tell something I hope you'll understand. The mass is determined by P1 plus P2 square. If I have an uncertainty of the energy, it easily can push the mass, can take it. Now, if you allow, when you do the fit, this uncertainty to play around, and if you combine both experiments, there might be a situation where the uncertainties will push each other, so you gain and you get a much bigger peak somewhere in the middle, okay? That's what the blogger got. So this brings me to my second nanostatistical interlude, which is, no, I don't have time. Okay, maybe I do. Okay, so I have the test statistics. This time I want to discover. So I test the background only hypothesis, the no Higgs hypothesis. So I generate Monte Carlo without the signal, not with the signal, and look at the test statistics. It will look like this. If there is no Higgs, most of my results will be here. It's opposite as before. If there is a Higgs, I will get something around here. This area here is called p-value. So the p-value can be translated into significance. If you use a Gaussian, you translate this p-value, this area here, by the, if you like, the famous functions, very easy to do, and you find how many significance you have. So I don't really have time to go into details here, but P0 will be the probability that your test statistics will sit very far from the background-only hypothesis, that it will make no sense. Okay, that is called P0. So the smaller the P0, you are less compatible with the no Higgs hypothesis, less compatible. The smaller the P0, less compatible. So you can easily say that P0 measures the compatibility of the data with the no Higgs hypothesis, okay? So if P0 is 0.025, the no Higgs hypothesis rejected at the 2 sigma level, we call it a discovery 2 sigma level. So P0 is the probability that our test statistic is incompatible with the background-only hypothesis. But the name of the game these days became the look elsewhere effect. So as David explained as well, the look elsewhere effect says, I can test my hypothesis at a specific mass. But had I seen a peak anywhere in the search mass range, I don't know where is the Higgs. Had I seen a peak anywhere in the mass range, I would jump and say, no, the Higgs is there, it's not here. But the probability to see fluctuation anywhere in the mass range is much bigger than the probability to see it only here. For years, people thought that this trial factor, this ratio between the probability to see it here or to see it anywhere is the search range divided by the mass resolution. I was lucky to have a brilliant student who worked out with me the look elsewhere effect, and the formula that is used in LHC now is this formula that was derived by me and my student to get the look elsewhere effect. Now, I don't have time to really go into it, but you have the archive number here. But the principle is very simple. If you want to estimate, when you see a result, what is the look elsewhere effect, you do the following procedure. You look at your likelihood as a function of the Higgs mass at some level, and you count the number of up crossings. And then you plug it into this formula here, and you get the look elsewhere effect. So this is what we use in LHC, both in Atlas and CMS. So here is the Higgs to gamma result. What you see here is that locally for Atlas at 126 GeV, this is the famous thing, you see a 2.8, I think, 2.8 sigma, a P0 which is so small, which will be like 2.8 sigma. If I will, no, I don't get that. Okay. A 2.8 sigma means if you look at the Gaussian, then what will happen is that if you look at the Gaussian, so what we see is that the observation is here, and that thing here will be 2.8 sigma, and that will be the P0. Okay? So that's what we see. Now, you go to the formula that I showed you, and you ask yourself, what is the probability to see 2.8 sigma or more anywhere in the mass range? Depends on the mass range. It depends on the mass range. If the mass range is big, you might have a very high probability, but that is not even sure. Because as you get away from the ZZ and gamma gamma, your mass resolution is much worse. So you don't have upcrossing if you think about it. So this is the probability becomes 1.5 sigma for the gamma gamma. 1.5 sigma is not something to write home about. Not something to write home about.
To get that, what range did you use?
That's the thing. Because that's what I tried to explain now, that because most of the upcrossings occur at the low mass range, it doesn't change a lot if you use the mass range up to 140 GeV or up to 600 GeV. The difference is very small. Because most of the effect of the Lucas effect is because of the ZZ, and in this case, it's because the gamma gamma is only relevant up to 140, 150 GeV. So that's the range we used here. But it's more relevant. The formula is mostly useful when you combine many, many channels and you don't even know what is mass resolution.
In Fabiola's talk, she said 100 to 600.
100, 600 is when we do the total, you'll see. Not in gamma gamma. You cannot do it in gamma gamma. You don't have gamma gamma at 150. Yeah, this is just gamma gamma. And that atlas versus CMS, CMS on top here. Yeah. What's going on? Okay. Okay, I already showed you the thing. Okay, let's look at it. That's atlas. That's CMS. You see that CMS sees it at 123 above 2.1, 2.2 sigma. Atlas sees at 126 about 2.8 sigma. And you can appreciate yourself what does it mean, okay? Yes, Zohar?
What happens if you don't include the Lucas effect in the regions that are already rejected anyway?
Well, that was the question, but he says that.
If I don't include the Lucas in the region, but nothing is rejected already between... But gamma gamma is not applicable above 140. You'll get the answer. You'll get the answer when I get to the end, if I get to the end, okay? You'll get the answer. Okay.
I see no crossings except the...
No, that's not the plot where you see the crossing. You'll see the plot with the crossing in a second. That's not the one. You have to look at the likelihood as a function of the mass.
Crossing.
That's P0. That's P0. When you check... I'll show it to you. I'll point to you where you count the crossing. It's not here, okay? Okay, I'm skipping because it's not, I'm skipping this. Okay, I will also skip this channel here. That's probing the WW. Since nothing interesting was discovered there, I'll just show you the event. That's a WW, goes to muon and electron and neutrinos. And this is really looks like when a WW goes to mu plus neutrinos, it looks really like a Higgs going to electron, muon, and neutrinos. So how can you tell between the two? Luckily, the Higgs has spin 0. Because of spin correlation, the angle between the two leptons coming from the Higgs is a little bit smaller than the angle when you have the WW. So we are able to separate them a little bit. For example, a top will give us also mu plus 2 B's plus neutrinos. So how can we tell a top from a Higgs? We do the same trick, but this time we protect against, we reject the top by require anti-B tag. So we have a B, that's no Higgs, okay? Okay, I will not go into this channel because I want to talk a little bit about it. I will go to the next one, which is the golden channel, okay? The golden channel is the Higgs goes to ZZ, goes to 4 leptons. This is clean, but very, very low rate, unfortunately. Yet probably it's the most trustable because you can fully reconstruct the kinematics and the masses of everything. This is, for example, an event here where you have 2 electrons and 2 muons. So what you do is you require 4 leptons with high momentum. They should be isolated. 2 of them should come from a Z. The other 2 not necessarily should come from a Z. And you should be able to tell them from backgrounds like ZZ, ZBB, Z plus jets, and TT. You suppress the background by isolation cut, impact parameter cut. And we have great understanding of everything. This is, for example, here you see actually the mass resolutions that we get to. This is where we have 4 electrons. This is where we have 4 electrons. So with simulation, we get to a mass resolution of 2.5 GeV here. When we have 4 muons, we get to 2 GeV resolution. We measure the electron efficiency, but what we call tag and probe methods. From J psi go to E, from W go to electron neutrino, from Z go to E. You see very little tension here, and everything, almost everything agrees. Here you see a little bit tension between the J psi and the Monte Carlo, but normally we are in a very good situation here. So this is the result. In the low mass range, we observe 8 events. 3 of them for muons, 3 of them 2e2 mu, and 2 of them for electrons. We expect 9.3 plus minus 1.5. In the high mass, so all the full range, which is from 100 to 600, we observe 71. We expect 69 plus minus 9. But the interesting region for us was in the region which was not excluded yet, which is below 141 GeV. In this region, we observed 3 events. You see them here. They are all concentrated here with a mass of 123.6, 124.3, and 124.6. In this region, we expect about 1.5 background events. And what you can see is that things are compatible, but somehow the statistics play the game with us, and all the events are concentrated in the same mass. If it's Higgs, it's too many. It's way too many, but not that much too many. This is the 3 candidates that we have. This is the electron-electron muon-muon with a mass of 124.3, and both these are off-shell. This one has a mass of 123.6. It's again a EE mu-mu. One Z is on-shell with 89.3 GeV, and the other is off-shell with 30 GeV mass. And the last candidate is the 4 muons candidate. Very easy to see the 4 muons here. It has a mass of 124.6. One is on-shell, the other is off-shell. So when we look at this, this is a tricky thing because it doesn't tell a whole story unless you combine it with the other channels. But if you follow the little bit explanation that I said, the explanation that I gave you before, you see that this, here you have an observer which is above the expected. You go to the data and you see this comes from here. Okay? Here at 240, we have again an observed much bigger than the excess, so big that we cannot exclude. It goes above the 1 and it doesn't enable us to exclude. Had we not have some history, we would have said we have a discovery here. And you see the excess here. Statistics plays a game with us. When we compare with CMS, the interesting thing is that both CMS and Atlas are not being able, although the sensitivity is way below, they cannot exclude the low mass because they see some excess there, okay? So CMS pushed their lower limit at 134 GeV, Atlas at 135. None of them, even though their expectations are below, which means that the expectation is below, they cannot make this, these exclusions. When we look at the P0, okay, now I need to explain something. This dashed line is what you would have expected had there been a Higgs at 110, 120, 130, whatever. What Atlas sees, you see here, is about 2 sigma at a mass of 120, 123, 124 GeV, about 2 sigma, which is above the expectation from a standard model. Had there been a standard model, we would have expected this P0. We see more than that, which means that we see a fluctuation even above the standard model. When you take the Lucas effect into account, all these fluctuations, they are washed out completely. This is CMS.
Sorry, when you do the LEE, what region do you take?
In the LEE, we tried, I think I wrote it here. In the LEE, we tried both regions. We tried the region of the low region until 140, and we tried the region until 600. Both of them are washing the effect out because the significance here is too low.
If you take the region from 115 to 140, you say it's washed out?
115 to 140, it's washed out, yeah. Because, okay, this is your reference level. What I called up crossing is the number of times you see this goes down. Not goes up, but goes down. So from 150 to 140, you see only about 1 or 2. You see 2 up crossings, but the significance, the starting significance is so low that it washes it out. If the starting significance would have been high, it wouldn't wash it out. It's because the significance that you have to start with is very low.
I really don't understand. It goes down once in that
Let's talk about the combination and ask the same questions there, because I will not get to the combination and I will feel that I didn't do my talk. Okay, that's CMS. CMS do see something interesting above 2 sigma in, oh, what did I do? Sorry. Yeah, CMS sees something interesting here, about 2.5 sigma or something like that, 2.7 sigma. But the funny thing is that the total expectation is 67.1 plus minus 6 events total. They see 72 candidates. They refuse to make a big deal out of it. They claim that if they do the Lukatz effect, whether you see that most of the upcrossing occurs in this region here, so whether you take 110 to 150 or you take the whole region, the Lukatz effect, they claim washes out the events completely. They claim that it washes it out. They are not even willing to discuss a possible discovery here. I will skip the heavy Higgs because I want to talk about the combination. Okay, let's talk about combination. So the first thing is we take all the systematics into account. Some systematics exist between the experiments themselves. For example, luminosity is common to all experiments. Cross-section uncertainties are taken from the Higgs working cross-section group and are taken common between the experiments. Some systematics are common between channels. That depends. Energy uncertainties, tau scale uncertainties, and many things like that. So all these things is taken into account in a very sophisticated machinery. And let's see what happens when we combine from Atlas. Okay, when we combine from Atlas, what we see is you have the channels here. That's upper limit. You have the expectation for the gamma gamma, the dash, and the observe. And you have here, for example, the tau tau, but it has very low luminosity. So what controls the limit is the gamma gamma here. And what you see here is the blue here is the 4 leptons. That's what controls. So when you put everything together for Atlas, this is what you get. This is what you get for Atlas, and when you put everything together. So Atlas is able to exclude between 124, the expectation is between 124 and goes all the way to 520, but the observed is divided because it starts from 112 to 115, excluded, when you go below 1. Then 131 to 237, and the third one is 250 to 453. So this is Atlas story. Atlas today is this thing here. So that's what Atlas still allows the Higgs to live is between 115 and 131. That's what the phase space for Atlas. CMS has done not only 2 channels. We did only 2 channels. CMS has done 8 channels. They were hurried. They did all. The real reason is because Atlas changed the software version about 2 months ago, and we had to generate all the Monte Carlos again, so we didn't have time, so we didn't finish it, okay? But CMS analyzed everything, and you see that their space left for the Higgs to live is very, very small. So CMS are leaving for the Higgs to live only a space of about, where do I have it here? About 114 to 127, something like that. That's the only space left for the Higgs to live in CMS. A nice thing came from CMS is that the CLS, remember CLS is the compatibility of the data with the signal hypothesis. If CLS is small, you are not compatible with the signal hypothesis. So this is a compatibility of 1%, which means that if that the region from here to here, which is 128 to 525, is excluded already at the 99% confidence level. So you can be quite certain that there's no Higgs between 128 and 525 GeV. It's the region from here to here. So this is 95% confidence level, and this line here is the 99% confidence level. Sorry, it's from here to here is a 99% confidence level. So as you go down, you see that you could still have a Higgs. You can also read it as saying that there's really not even a Higgs lighter with a strength lighter than the standard model. You really killed completely a large region of the possibility for the Higgs at very high confidence level. Now, this is a blogger spot. I don't show you the blogger that David showed. I showed you another one, but I cannot tell you where it comes from. But this is done in the right way, that I can assure you.
Is that anonymous bloggers?
Anonymous bloggers, okay? Anonymous blog. And what does it mean, since I don't have time? First of all, you see something interesting here. Observe Atlas, observe CMS. When you combine them, because one observes upward fluctuation and the other observes exactly this space downward fluctuation, the total is actually below. And you see, again, you see the 4 sigma, that's 1 sigma. You see, you go from green to yellow to red and to ultraviolet, okay? So this is where you see. So what you see is actually, this is important to say that actually we exclude the X from 127 above, and there could be X before. The interesting stuff will be with P0. That's where we want to really do a real work here. So when we combine Atlas, we have various channels. The gamma is the red. The 4-lepton is the blue. When we combine them, we get about 3 point something sigma. Where do I have it here? And here is your answer. The global P0 here, over the mass range 110 to 146, will be 0.6%, which is 2.5 sigma. And over the range 110 to 600 GeV will be 1.4%, which is 2.2 sigma.
Why do you do that? If you told us now that the Higgs has been excluded above 128, 140. Okay. The answer is very simple. Atlas is an experiment on its own. From Atlas' point of view, 141 GeV was the region of search. But you go up to 600, up to 600.
We give information. That's a result, because as I told you before.
It sounds like you don't believe your exclusion.
Look, exclusion is a 95% confidence level. I told you that the 240 GeV, for example, we excluded before, and now we cannot exclude. So we have to take into account possible fluctuations. We have to give to the public all the information. But let me go to the interesting stuff here, and then we can go back to it. That's when I compare Atlas and CMS, and I look at them one side by side, okay? So you see, the 126 of Atlas is this point here. If you go to CMS, you see that it sits on around 1.8 sigma here. The 124 of CMS, in Atlas it sits in the middle of here around 2.7 sigma. In CMS it gives you the 2.5 or something like that sigma. Another CMS also observed in the 4 leptons a fluctuation in 119 GeV, which was our favorite mass range. I must tell, to be honest and tell, that the 119 and 125 GeV are our favorite masses for the Higgs for a long time now. We also saw traces of this in the lepton photon. If we can go back and I can show it to you. But anyway, so this is the picture as is. Atlas is nothing at 119. But you see something very close around 123 and 126. So
Again, the mass resolution is 2 GeV.
the mass resolution is about 2 GeV, 2.5.
You know, so it would be a lot more, since you're taking care, so careful.
Let
If you
me-
were to draw that resolution of the
But you see, the mass resolution is reflected by the width of the peak.
No, but it could be reflected in the width of the lines.
No, not in the width of the lines. Okay. Then if I do this, it will look. But I do it in a second, in a blogger spot, in a second. Okay, here you are. Okay. So this forbidden apple shows you actually the combined P0, Atlas, CMS together. So you see, we see, so now, the interesting line here, which you saw, the blogger didn't know how to do it, but that's the interesting line, is the dashed line here. The dashed line shows you what would be the P0 expected if you do a lot of experiments with the signal inside at this specific mass, what would be the average P0 that you would see. So what you see here, that when you put both experiments together around 124, 125, you have something which is compatible also with what you would have expected from a Higgs at that range, okay? Now, this is the interesting plot, and this is the upcrossing that I was talking about. You take the level here and you count the number of upcrossing. That's the upcrossing I was talking about, okay? Now, what is this? Mu hat is the maximum likelihood estimator of the signal strength. Maximum likelihood estimator of the signal strength when you look at the likelihood as a function of mu and b. And what is mu? Mu s plus b is actually your expectation, okay? So this is Atlas, the full mass range. This is Atlas low mass range. So, and this is Atlas gamma gamma. The way you read this is the following.
Had there been a Higgs, and I did not say that there is a Higgs, so don't quote me saying such a thing, because I'll be fired on the spot. So had there been a Higgs, that means actually that Atlas observed a Higgs at 126, which is 1 sigma above what you would have expected from a standard model Higgs, which is completely normal. And it's many more sigma, it's 2.5 sigma above the background only, okay? But if you look at the gamma alone, we see that the expectation in the gamma, the observation in the gamma is 1.5 sigma above what you would expect from the standard model Higgs to gamma. That's what it means. That's the mu hat, and that's from CMS. So you cannot ignore the fact that CMS do not have such thrilling and striking results in Atlas. They don't really observe, but in a way they shouldn't, because we see an upward fluctuation even with respect to the signal itself. So CMS sees a signal which is compatible with what would you have expected from the standard model around 123 GeV. So now the thing is, what happens if you put these things together? So you see the following. You see around 125 GeV, something which is completely compatible with the standard model Higgs. And the 119 of CMS is seen as that could be a Higgs, but this Higgs wouldn't be a standard model. It would be like a SUSY Higgs with a strength of sine square alpha minus beta, a strength of 0.7 or something like this, okay? Now, what can we do with all this? There are two scenarios here. Scenario number 1. We see just a standard model Higgs, and that's it. Not much leaving space for the Higgs. I played on this famous plot of LEP, and that's about what was left, not much. This plot is very, very well known. It appeared first with Manfred Lindner, Mark Scher, and all this company in 1989, and the latest version, but not the most latest, from Ellis, Spinoza, Guidice, and they have a paper from a few days ago, 2009. So now I'm not talking as an expert, I just show you, you theorists do with it whatever you like. You see that if you believe the desert assumption, if you believe this plot, we excluded already the vacuum stable region, so which means if there is a Higgs at 126, it's either not a standard model or a vacuum is metastable. But that's probably not the case, because two papers came out. One of them came in December, when was it? December 13th. I think it was, this one came exactly at the date of the CERN seminars, because the rumors were all over around. So you have here the top mass. Where is this? You have here the pole top mass. You have the Higgs mass here, and that's all the stability regions. So in short, let me tell you, they say that probably if there is a Higgs, our universe is metastable, but there are some conditions in which the Higgs can still be there at 125 or something like this. It was before the seminars, 125, and the universe is still stable. And Manfred sent me, he's a friend of mine, so he sent me this thing, but I didn't tell him the results ahead. And he actually published it on 12th December, a day before the seminars, and he has this, I call it hallucinative plots, where he says, okay, suppose that the Higgs gets his mass only by radiative correction, so the lambda coupling is 0 at the Planck scale. I'm sure you understand, most of you understand better than me what I talk about now. But his point is that the vacuum can still be stable with the Higgs with a mass of 127 plus minus 5 GeV. So you have the archives of both of these fascinating papers, but there are probably another tens of thousands of papers. So nightmare scenario number 2, which we should take into account, that next summer we exclude the Higgs. There's no Higgs. There's no Higgs. This is a real nightmare for us, the experimentalists, because we will not get any more money. This is a real nightmare. But for theorists, this is and Zohar is smiling already. This is a great thing if you see no Higgs. You have a car that's driving in the speed fantastic and smooth, and there's no engine inside and it's still driving, you know. So how is it driving, you know? Okay, I want to finish my talk with 2 quotations from a paper from 1976 by my hero, John Ellis, and he's my hero because he's really funny and he knows a lot, and I can always ask him questions and he's always happy to answer. So, in 1976, he wrote the following with his partners, Anopoulos and Gayan. The situation with regard to Higgs boson, this is supposed to be amusing, so don't take it seriously, okay? The situation with regard to Higgs bosons is unsatisfactory. First, it should be stressed that they may or will not exist. Higgs bosons are introduced to give intermediate vector boson masses to potential symmetry breaking. However, this symmetry breaking could be achieved dynamically without elementary Higgs bosons. Thus, the confirmation or exclusion of their existence would be an important constraint on gauge theory model building. Unfortunately, no way is known to calculate the mass of the Higgs boson, at least in the context of the popular Weinberg-Salam, 1976, and they end the paper in the following way. We should perhaps finish with an apology and caution. We apologize to experimentalists for having no idea what is the mass of the Higgs boson, unlike the case with charm, and for not being sure of its coupling to other particles, except that they are probably all very small. For these reasons, we do not want to encourage big experimental searches for the Higgs boson, but we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn up. My conclusion. 2011 and 2012 were actually the Higgs and LHC miraculous years. Will be. One of them was, one will be. Whether we find the Higgs, it's a discovery. Whether we don't find the Higgs, it's a discovery. The standard model Higgs, if it's there, it's probably light, something between 115 to 127 GeV. I think from any point of view, standard model, exotic, SUSY, Higgs, this is the prime time for any high energy physicist. What are the plans? We are in a shutdown. In April, we will start one again. We hope that we'll get about 20 inverse femtoband per experiment. That's what we need in order to get a 5 sigma discovery for 125 GeV. Atlas or CMS alone. If we get less, we can combine, but we prefer to get it per experiment. There's also talks, and there's a very high probability, to my mind, that the energy will be raised to 80 eV per experiment, which gives us about 10% sensitivity, which means that our lines will just go down by another, the expected lines, the dashed lines will go down by 10%, which will allow us a little bit more. Thank you very much. זה שמה. בחדר מצד שמאל. היא לא אקטית? Shouldn't give lectures on board.
Okay, Eilam,
Yes.
just a quick comment. You showed this, what you call hallucinating plot.
I don't understand about this. I just showed it because I thought it would interest you.
I understand, but you said that it was sent to you a day before the seminar.
Yes.
However, it should be pointed out that the value of the mass has been floating around at least 2
I
weeks
said they
before.
probably read the blogs. I said it. In both of them, the Guidice and company and Manfred. I agree. But Manfred said thank you to me in the end, and the other did not. That's the thing.
Further questions?
Yeah.
Please.
So to get signals with more sigma, would they violate the standard model Higgs even more?
Yeah, that's a good question. I was hesitating if to say it or not. In a way, it's possible that we exclude here, with only the Atlas result, the gamma-gamma, both the standard model without the Higgs and the standard model with the Higgs. But we exclude more the standard model without the Higgs.
Is it correct that precision measurement requires something like Higgs?
I'm sorry, what?
Precision measurement.
Yeah, precision measurements, yeah. You know the answer of the precision measurements.
Yeah, but they require some kind of particle, right?
They require light Higgs, yeah?
Yeah, they require light Higgs. So
Yeah.
if you exclude light Higgs next year.
And that's what I said. That's a nightmare scenario for many of us.
No, but it's actually direct contradiction.
Well, there's a lot of theory that goes into it.
There is a lot of theory, but what would be the simplest theoretic for this scale?
I don't know the answer to this.
Come on. It's not a question for an experiment. Why? Could you explain to me what, when you exclude the Higgs,
Yeah,
you're happy with a 2 sigma exclusion?
yeah.
When you discover the Higgs, you're
Okay.
unhappy with almost 4 sigma.
Okay, yeah, I can explain to you because you already said, I had time to think about it because you pointed out something about the 5 sigma in your previous talk. So actually, I heard that the answer, I'll answer you by the discovery. So
The thing is that I learned it actually from a workshop which I attended in 2000, and Gary Feldman told us some historical introduction to statistics in high-energy physics. And he talked about the Lucas effect, and that's the first time I heard about the Lucas effect. And he used then the wrong formula, but intuitive one, of the range over the mass resolution. And he showed that if you really want 3 sigma to be your criterion to detect the Higgs, if you take the Lucas effect into account and you allow the Higgs to be anywhere, because at that time we knew nothing, you get that you need a 5 sigma. So that's the history of the 5 sigma. You know probably much better than me that in astroparticle physics they use even a less stringent criteria for exclusion. They use 90%, and for discovery they'll be very happy with 3 sigma. And so it's arbitrary, completely arbitrary. But I must tell you, okay, maybe I shouldn't, I don't know. We've seen, okay, let me put it in politically correct way. We didn't publish it, but we have already seen in Atlas and CMS 3 and 4 sigma fluctuations that went away. So I think there is a human bias which you don't take into account here. That you start to see a peak and you start to, to dance with your energy uncertainties and you're happy. We don't do blind analysis in high energy physics. We do them in dark matter physics.
No, they do.
No, not in Atlas and CMS.
Not in Atlas, but high energy physics is not.
For me, high energy physics is Atlas and CMS.
No, but for this you couldn't do blind. These are part of it. Let's just do them. Yes, please.
I think this was on the blogs here in some way, the conceded arguments, but I thought the interesting question I had from reading that is how is the look elsewhere effect changed by what some people would say are reasonable theoretical biases that amount to the statement that you believe in quantum field theory at the energy scales that your experiment is operating at?
Okay. The answer to this is that the formalism on which all the formulas are based on, including the exclusion, the P0, and the Lucas effect, we use a test statistic which is the profile likelihood. The profile likelihood is made of the parameter of interest, which is signal strength, the Higgs strength, and the rest is what we call nuisance parameter. The nuisance parameter include all the theoretical uncertainties that you talk about. We put them there. So when you check the likelihood as a function of the Higgs mass, what you'll see is that it reflects the nuisance parameters. If all the uncertainties that you talk about will change the number of approximations that we will see, and will actually increase or decrease, depends on the uncertainty, and will be taken into account the calculation of the Lucas effect. How? I don't know. That depends on the uncertainty. Okay, for example, if it's energy uncertainties, it will do 2 things. It will increase your signal, and you will see much more than the 4 sigma that we see. But on the other hand, it will increase the Lucas effect in such a way that it will compensate each other, and the global p-value will be the same. Maybe that's the answer to the question that you asked. You can play the games, but what you'll do is you'll increase your local significance, but you'll increase also your trial factor, so your global significance will remain the same. Did it answer you? Sorry?
I think I need to think a little bit about what you said, but I guess what I was trying to say in a little bit more conservative language is that you expect, maybe, at least I don't know enough quantum field theory to speak to, you expect something, right, to give you, we've seen that Z, W, and Z masses, right, so we know that it has to be something to break.
Well, that's what David said, that we have already seen the Higgs, but we use frequencies. Maybe that's the answer you were looking for. We use frequency statistics, not Bayesian statistics, though every result that I showed you here was conferred also with Bayesian statistics. The difference between frequency and Bayesian statistics, that in Bayesian statistics we can put any prior that we like. So one prior, and the prior is actually could be a degree of belief. So I could insist that there is a Higgs boson in my prior. I could insist it, and then your question would be, how will this insistence affect? But that's what you do with G-fitter, okay? You actually insist that you have a Higgs boson, and you try to fit and say where it is. So you know the answers. The answer is that the Higgs actually should have been lighter than what we observed already, and we didn't see it. So we put a penalty function, we push it up, and now we expect the Higgs to be around the 125 or whatever.
But all these papers that I showed, the Guidice and the Manfred-Lindner, etc., are in a way Bayesian papers because they have a prior that the Higgs is at 125 GeV and they don't tell it to you specifically.
If you manage to discover this particle, how do you know that this is
This particle, the Higgs boson, yeah.
Yeah, how do you know that it's a scalar?
That's why I'm happy that I'll be the Higgs continuum for another 2 years, not only 1 year. Because then the name of the game will be to start measure its priority. So you look at angular distribution, etc. But I can already tell you that if you don't see the Higgs, the first thing you want to do is WW scattering somehow.
Maybe a more technical question about photon isolation. So to beat back down the background, hadronic background, I assume you do isolation. But,
Of course. In a cone, we require that there will be no energy besides the photon in a cone of delta, what we call delta eta of 0.4.
And the numbers you were saying, like even one pion in what is 10 to the 5th, that includes all the isolation.
Of course, that's the whole trick. Okay, CMS are managing to do it even without pointing geometry in the calorimeter. So they can do it even with isolation only. We don't win that much, but we win something, you know.
I have 2 questions to you. The first, Tonelli told me that they had W fusion events, which you said are very difficult to see.
I can show you. I had it in my talk. I skipped it.
You skipped, and they withdrew them a day before the seminar.
No, they have a vector. You talk about vector boson fusion events.
Yes.
They have a beautiful vector boson fusion, but anyway, I can show it to you, but it's... it's one of the most beautiful events that I've seen in my life, so that's why I put it in my talk, even though here it is. Okay. You see 2 forward jets, and it's a VBF with candidate for Higgs to tau tau. You do the 2 forward jets, no activity in the central region.
He said it's in the range that you saw this.
No, that's not the one. That's not the one. That's not the one. Okay. No, I don't know. I have not seen this one.
The second question, I'm willing to waste 50 shekel to make a measurement. And my measurement is, I will let you win a bet. If you make a positive prediction to where you believe the Higgs mass is, I'll bet against you. So I give you the priority.
I already made a bet with the Higgs convener of CMS, and that was the time when we believe it's 119. But now I don't think it's 119. Now I think it's 125. Come on, I'm not.
You already said
125.
He didn't say.
125.
Okay. So we made the bet.
Plus or minus.
Yeah, but what is the bet about?
50 shekel.
50 shekel, come on.
That's fine. Okay, so I think we convene again at the top of at the half hour.